Hello again, everybody. Today I'm going to be completing our last video lesson for the course, and this is going to be wrapping up Chapter 7, and we're also going to touch upon a little bit of Chapter 8, and then that's it for this semester. So anyway, we're going to continue on with arrays again right now. And what we're going to do is we're going to cover an important topic. It has to do with what's called parallel arrays. All right. What a parallel array is that oftentimes you have data, okay, that needs to somehow be synchronized with other data. There's kind of other ways to do this, and you'll learn more about this later if you can continue with computer science and look at other languages, or if you continue on with C++ and you'll learn a little bit more about how structures work and classes work. Um, but nonetheless, for the time being, so based upon what we know so far, all that we have access to is arrays. And if we want to keep track of data that's related to one another, but they're of a different type, how do we go ahead and do that? So here's a little example where we have three different arrays. So the first one is a string of arrays. I'm sorry, it's a string array that's called names. All right, and I think I mentioned to you in the last video lesson that arrays aren't restricted to being of any of the primitive types. All right, you can also use arrays of any type, whether they're object types or structure types. So in this case here, we have a type that's a string. Remember, a string is a class where you create strings as an object. So names is an array of strings. All right, and then we have some related information below it where the corresponding hours that perhaps somebody worked is represented in a different array, which is of a different type. This is an integer, right? So the integer array called hours has three different values, and those values are related to the people that belong in the names array. And then in the third array, you have an array that's called rates. It's of type double, and this corresponds to like the hourly rate or whatever that somebody receives as their pay. So sort of the problem that we're trying to solve here is that we have this information. This information is all related, but how do we go ahead and process and manipulate this type of data? And this is something that you're going to need to do in the for the final lab. And I think this is a good example to demonstrate that. So imagine all that we want to do is, we read in this data, we store it in some arrays, and then we want to go ahead and just display these values. Well, I could create a loop. All right, my loop will go through each of the elements in the array. How big is the array? Well, I know that each array, I'm sorry, how big is each array? Each array is of the same size, which is defined as the constant size. So I know it'll be subscripted from 0, 1, and 2. And what I can do is as I iterate over my for loop, I can extract out each person's name or each employee's name, each employee's hour that they worked, and each employee's rate. Okay, I could then go ahead, if I so choose to, I could calculate what their pay is going to be, right? So their pay is going to be just their hours times their rate. Once I'm done with that, I will have processed the first employee. All right, then I could go through and do the second and the third, and if there was more, you could continue on. So that's the general idea as to how we keep these guys related and synchronized with one another. Another thing I want to mention too is you might be wondering, why do I have this declarator here that's called size, but I don't have it within my subscript notation here? The reason is because here in each one of these arrays that are declared on rows 8, 9, and 10, as I'm declaring the array, I am also initializing the array with some values. So in this case here, since we're doing that initialization when we declare the array, the compiler already knows that there's 3 elements here, there's 3 elements here, and there's 3 elements here. So if I wanted to, I could do this. Okay, I could say that it's of type size, but it's not necessary. All right. Nonetheless, so when I go ahead and I run this thing, we can process the build succeeded. And if I run this, you can see that it will display each employee's name, the number of hours they worked, their pay rate, and also their gross pay. Let's call it gross pay. And then we would iterate through each one of them. So anyway, that's how we keep track of parallel arrays. For today, I need to kind of keep this video a little bit short, this lesson a little bit short. So I'm going to skip over the section actually, I'm going to be skipping over two sections. One section is going to be dealing with two-dimensional arrays. All right, I would suggest if you have time, look into that. Two-dimensional arrays are, it's not uncommon to come across them. You can also create three-dimensional arrays. That is something that is less likely that you're going to come across. But there's also a topic, and maybe I'll flip to my book real quick here. In sections, I believe it's 7.12. I think it's about page, maybe it's about 429. I'll briefly explain it, and I would, if you have time, it might be something that you want to look into and play around a little bit. All right, so in C++, they have a container, okay, which they call a vector. What a vector is in C++ is it's something that's very similar to an array. However, it has one distinct advantage in the sense that a vector is a data structure that can grow and shrink as items are added to or removed from the vector. So remember, I think at this point you probably see what the usefulness of using arrays. However, you might have already seen that there is a restriction, and the restriction is that once you declare that an array of a particular size, that's it. Okay, that's the size that you specify, and it can't grow and it can't shrink. The vector is different. Okay, it can grow and it can shrink. A vector is something that's part of what's called the standard template library. Usually it's just referred to as STL. Within the standard template library, there's a bunch of other containers and what are called algorithms that would allow you to do things like add elements to a vector. You could do a search within a vector for a particular item. You could do a sorting of a vector. A lot of different things that you can do with vectors. And it's just one of the components, and it's typically what's referred to as a container. It's just one of the containers that's part of the standard template library. Definitely would look into this a little bit if you guys have a chance, especially if you're going to move forward in computer science. And the concepts of a vector, it's sort of generic, meaning that other languages such as Java have something that is very, very similar, okay, but it just uses obviously as a different syntax, but nonetheless it has the same type of look and feel. So anyway, that's it for now. Again, I wish we had time. We could pursue that, but what we need to do now is talk about some of the algorithms out of chapter 8. All right, this is the last bit of stuff that we're going to do for the course. And this has to deal with what are called searching and sorting algorithms. So the idea is that there's a lot of different ways that you can search for values within a list of items, and there's also a bunch of different ways that you can sort a list of items. All right, we're going to summarize this into one of two different categories for each one. So we're going to first implement what's called a linear search, and then we're going to perform a binary search. So there's going to be two different searching algorithms, and then we're going to perform what's called a bubble sort, and then a selection sort algorithm, which will allow us to sort a list of data. There's a lot of different other algorithms that you can use for searching and sorting, but this is a good place to start, and I think both of these categories illustrate the differences between the two. And just so you know too, in case you're unfamiliar with the word algorithm is just nothing more than a sequence of instructions, or you can think of it as a recipe. Sometimes people refer to that as a recipe. So again, an algorithm is just a computer science term that's used for a set of instructions. So let's go tackle the simplest one first. Here I created a couple prototypes for both my searching and my sorting algorithms. And the first one is my linear search. And the prototype it's going to return okay, what it's going to return is actually the position within the array where it found the item, or -1, which is an indication that something was not found, right? Because again, the idea is you do a search, your search may be unsuccessful, and if it is unsuccessful, you need to have some kind of indication to that fact. Here are and then obviously it's called linear search, and here are the parameters that we're going to be passing into our function. This is something that might be new. I don't think I covered this yet. So we know what if we want to pass an integer array, we specify int with the square brackets within our prototype. But we also can optionally pass in the specifying that the parameter is a constant. What does that mean? Remember from the last lesson that when you pass an array to a method to a function, that array is being passed by reference, or actually is being passed by memory address, meaning that any changes you make to that array will be reflected outside of the function call, all right, because it's not passed by a value. What you can do is you can specify in your prototype that the array will not be changed, okay, meaning that it's going to be a constant. All right. So since we're doing a search of an array, it would make sense that we don't want this linear search method to go ahead and change the values of any of the elements within our array. So what we can do is we can use a const keyword, which will do two things. First of all, it'll ensure that who's ever calling this method, they will know that we will not change the array on them. And number two is when you go ahead and you implement the linear search method, if you inadvertently try to change a value within the array, the compiler will complain, and it's a good catch for you. The second parameter that we're going to be passing in is just the length of the array, and then the value that we're searching for. So let me first go ahead and provide the implementation. I think this one is pretty straightforward. So this is going to do a linear search. Search can be array, can be sorted, or meaning that we're going to process the search algorithm, and the array that's going to be passed in does not need to be sorted. A little bit when we do the binary search, you'll see that that's not the case. It has to be sorted. So anyway, let me do my little copy paste here. Copy this guy down. Linear search. Linear search. All right. So we're going to be searching my array for of a particular size. Searching for a particular value. So what we're going to do is we're going to set up a couple flags up real quick. First, we're going to initialize a variable for the index. Okay. We're going to initialize another variable, which is going to be the variable that's going to hold where we found the value, okay, within our array. So it's going to this variable here is going to be returned at the end of our function call, and it's going to be the indication as to where we found the value within the array. If we don't find the value, then position is going to remain -1, and we'll return -1. And this little guy here, this is going to be used in our while loop to determine or hold whether or not we've found something or not. So here's the general flow of the linear search. Since it's as the name kind of specifies, right, we're going to start from the beginning and linearly go through our array until we find the value that we're looking for, or we hit the end of the array. All right, one of those two things is going to happen, right? Either we're going to find the value we're looking for, or we're going to hit the end of our array. So this is a good candidate where we can use a while loop to process or iterate over each one of those elements. So here what we'll do is we'll just say as long as index is less than the length of the array and not found, meaning as long as we haven't found the item that we're looking for, right? Let me put my little comment in here. And here I'm going to do my little test. I'm going to say if the index of the value at my particular index, if that's equal to the value I'm looking for, right? Then what we're going to do is we're going to say why is it complaining AAR subscript I? Sorry, not I, it's index. Sorry. If if the value that I'm searching for is found at this particular index, then what we're going to do is we're going to set this flag that's called found. We're going to set that equal to true. This will prevent my loop from executing any longer. All right. And I'm also going to specify that the position is equal to index. All right. Because at the end, what I need to do is where position at the end of my function here, I need to return an int. In this case here, I'm going to return the position. All right. If this never evaluates to true, okay, right? If line number 21 never evaluates to true, then my position will remain -1. Okay, so we'll just return -1. The very first time that I find, okay, the very first time I find the value I'm looking for within a particular index of my array, I'm going to set found equal to true, and I'm going to store where I found that value, okay, which is at the index, and store it in position. The reason why we're setting found equal to true here is that this is, I mean, technically you could optionally leave this off, but what this will do is that as soon as you set this to true, okay, if found is equal to true, then not found will be equal to false. All right. So remember with the logical and, anytime you have something and false, it will always evaluate the entire expression will be evaluating to false. And in this case here, my loop will no longer continue to execute. So imagine that I have, an array with 1,000,000 items in it. And imagine that the value that I'm looking for is found at the second index within my array. Well, instead of continuing on for the remaining values within my, the other 998,000, blah, 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 999,000, so on and so forth, values within my array, what I can do is I can stop because I know I found what I'm looking for. Don't look any longer, okay, and then just return a position. So this greatly will improve the efficiency of your algorithm if you terminate the loop as soon as you find the value that you're looking for. Again, there's times when you can do this and other times when you can't. Imagine that you're looking for the number of values. Well, in that case, you have to iterate through the entire loop. Or if you have a really small array, then it's the performance is really insignificant. Anyway, so this should work. All right, this will return the values that I'm searching for. Let me go ahead and let me create a little. I'm going to create an unsorted array here. Array. Let me initialize with that. Initialize it with some values. 10. 5, 30, I'm just making things up here, 20, 50, 40. So there's my unsorted array. While I'm doing this, I'm going to create another array which is going to be a sorted array with the same exact values. However, they're going to be in sorted order, so it's going to be 5, 10. We're going to use this in a minute, so I figured it's just easier just to do it now. 20. 30, 40. All right, sorted array. Right. Now what I'm going to do is I'm going to create another local variable. Let me give it some more space. And create another local variable. I'm just going to call it POS for position. Here, let's do this. The size of my array, how many values are in here? There's 6. 6. And let's do this. The value I'm looking for is equal to, and I'll just set this as 40 right now. And just be consistent, I put my constants up here. And now what I'm going to do, I'm going to say my position, or my variable POS, is going to be equal to, I'm going to invoke linear search, passing in I'll pass in the unsorted array, the size of the array, and then the value that I am looking for. Okay, and here what I'm going to do is I'm going to do a little testing and say if position is equal to -1. Well, that means that we didn't find what we're looking for. All right, so we're going to have a little statement here, cout not found. Else, that means that we did find what we're looking for. I'm sorry, if position is not equal to, I'm sorry, not negative exclamation point, -1. All right. Else we're going to say, let's copy paste this guy down. Else we're going to say, okay, yeah, I did find it. Not only did I find it, but it's found at position All right, and that will tell us the where we found the value we're looking for. So the first time around, the value we're looking for, which is 40, that should be found at position what? If I'm passing in the unsorted array, all right? If I'm passing the unsorted array, that should be found at position 5, right? 0, 1, 2, 3, 4, 5. Let's see what we get. Seems like I have some kind of info loop here. Let's see what's going on. So linear search, unsorted value, length value. Looks like it should be working once this problem here. And while index is less than length and not found, return position. All right, something's not working. My method's not returning. Seems like I'm in some kind of infinite loop here. No, let's debug this thing. No, we don't have time to learn the debugger, but all right. I'm just going to put a little CS statement here. Searching for all right, searching for the index. Let's see if this helps. Searching for 10. So okay, I made the classical mistake. All right, what did I forget to do? Well, I forgot to increment the value of index. So since I'm not incrementing the value of index, this will always be 0. All right, and that's no good. So what I need to do is before my the invocation of my loop, once again, I just need to increment the value of index. All right, increment the value of index, and that should fix the problem. So that's what we call in the business a stupid mistake. Let's run this thing again, and it says 40 not found. All right, I must have made another stupid mistake. Not f array position is equal to index. Return position is equal to index. Position. All right. 2 stupid mistakes already. What's the problem here? Right here, I'm assigning -1 to position. All right, I don't want to assign -1 to a position. All right, I made another classic mistake. You need to test if -1 is equal to position. Here's a good strategy and to prevent yourself from making that kind of mistake. If you get into this habit, which I never did, all right, and if you do something like this, if -1 equal to POS, okay, if you make that mistake, the compiler, okay, will catch this for you. Because what happens is by doing this, right, if I put my what's called my L value, if I make my L value a constant, okay, I can never assign to a constant. So if you get in the habit of doing that, you won't make those types of mistakes. Most people don't do it this way, including myself. So we tend to make those mistakes once in a while. So here, what we do is, if we want to use if we want an L value to be, or a left value to be a variable, then we need to make sure we use a double equal sign. By the way, I teach the corresponding Java class for this course. That type of error that I just made would be caught by the compiler. The reason is because in Java, that what I had just done before, where say POS equal -1, that doesn't evaluate to a Boolean expression, and it would be caught for you by the compiler. So again, one of the advantages of using Java for this kind of stuff. Anyways, here finally I get the right answer, and it says 40 was found at position number 5. Let me go ahead and I don't know, let me change the value that I'm searching for from 40 to 140, and now I should not find it in my unsorted array, and it should return the value of -1, and it just says that 140 is not found. Why? Because the linear search function returned a value of -1. All right, the next search algorithm that we're going to take a look at is what's called the binary search. In the spirit of saving time, because we've already kind of been going for almost half an hour here, I just copied and pasted this from the previous examples I had from the other course, so I don't make any more stupid typo mistakes. And anyway, so here's how the binary search works. All right, the binary search is a very efficient algorithm when your data set is sorted. And it's put into a category that's referred to as a divide and conquer algorithm. And the idea works like this. So imagine that you have an array, and I wish I had something I could illustrate this a little bit better with, but we'll just read through the code. So imagine you have an array that's sorted from beginning to end, and you're searching for a value in the array. Well, there's a couple properties that we know of in an array that we can use to our advantage. First of all, we know that the array will be sorted, and we also know what the length is of the array, and we also know what the value is that we're searching for. So what we could do is, instead of starting at the beginning of the array and working all the way through until we find it or hit the end, let's look in the middle first. All right, this is why it's called the divide and conquer algorithm. So what we do is we look at the middle of the array. All right, if the value that we're looking for is at the middle of the array, then we found it. We found it on the first try. If it's not, well, we then have another set of property, or we have another property that we can look at, in the sense that since the array is sorted, we know that if the value that we are looking for is not in the middle of the array, but is less than the value at the middle of the array, well, then it must be in the first half of the array. Since we know that, we don't need to look in the right half anymore. We can throw that whole thing away, essentially. If, on the other hand, we're searching for the value in the array and it's not equal to the middle, but it's greater than the value in the middle, well, then we know that it's not in the left half of the array. What we can do is we can throw away essentially all those values that are in the left half. We don't need to look there anymore. And what we do is we basically just continue that process, breaking the array in half over and over and over again until we either find the value that we're looking for, or we don't find the value. Okay, and this is an extremely efficient array in the sense that we can look for, and you know, we don't have the time to cover all this, but I might have to take this on a leap of faith, or do a lookup on your own if you want, or actually it's probably covered in the book. Is that you could have an array with a million values in there, and at most it would take you 20 tries to find the value that you're looking for. you could have an array with, I think it's about 4 billion values in there, okay? And at most, it would take you 30 tries to find it. And this all has to do with the logarithm base 2 of searching for a something that's raised 2 to the power. Anyway, so let me step you through the code here and just kind of explain to you how this works. So here we have a couple of variables. One is going to be what's the beginning of my array. What is the end of the array? Right, the end of the array is going to be equal to whatever the length of the array is minus 1. So beginning and end is going to be, there are going to be some positions that are going to be moving around. And also there's going to be value, okay, which is going to be for the middle of the array. Well, actually, what I mean by value, meaning like index location. We also have a variable, once again, for position, which will return the value in the array that the value was found, or -1. And we have another variable here, false, just like we did before. And here's the logic of the binary search algorithm, and it's pretty well compact. And I think if you read through this for a couple times, you'll understand how this works. So what we're doing is saying while beginning is less than or equal to end. Okay, so the first time around, beginning will be less than or equal to end because beginning is equal to 0. Okay, if beginning is equal to 0, and in this case here we're passing an array of size 6. Okay, so the length, so n will be equal to 6, right? The length of the array minus 1. I'm sorry. N will be equal to 5, right? Because the length of the array is equal to 6. 6 minus 1 is 5. So this will be true the first time around. And of course, the variable is not found, right, is equal to true because we initialized found the false, so not found is equal to true. And what we do is we're going to say, okay, let me find out what the middle of my array is right now. So if I take beginning plus end, okay, and then I divide it in half, okay, that will tell me what the value is of the middle of my array. And this works true whether or not it's an even or odd size array. Okay. If the value that's in the middle is equal to the value that I'm looking for, well, then I know that I found the thing that I'm looking for. And if the position that I found the thing is equal to the current location of middle, all right? If this is not true, okay, then what I'm going to do is check to see, okay, is the value that's at the middle position of my array, if the value at the middle position of my array is greater than the value that I'm looking for, well, then I know that the value that I'm looking for has to be in the lower half of my array. I can essentially then go ahead and disregard ever looking in the right half of my array. And I'm now going to reassign the variable that's called end. End is going to be equal to the current position of where middle is minus 1. All right. If this is false and this is false, okay, the only thing that can be true is that the value that I'm searching for is in the upper half of my array. And now what I'm going to do is I'm going to move the position of begin, okay, is going to equal to wherever middle is right now plus 1. Which means I no longer need to look in the lower half of this array any longer. We jump down over here, come back up to the beginning of my while loop, and now, okay, if my loop is going to iterate, again, what's going to happen is either begin or the position of end has changed. All right. At some point, begin could become greater than end, and if it does, okay, that means that the value that we were searching for was in fact never found. Okay, this loop would no longer execute and we would return position, which would be equal to -1. However, as long as begin is less than or equal to end, we're going to keep dividing our array in half, searching for the value in the middle. If it's not in the middle, is it in the top? Is it in the lower half, or is it in the upper half? And we're going to keep doing that, breaking our array. Well, actually, we're really not breaking up the array. We're just moving our positions within the array over and over and over again until we either find the thing we're looking for or begin and end swap. Okay, meaning end becomes less than begin, where begin becomes greater than end. Once this is done, okay, we will have the value that we are looking for, or either the position will, we'll either have the position that we're looking for, or position will be equal to -1, which means that it's not found. I would recommend, and you're going to have to do something like this when it comes time to do the final lab, is when you pass in an array, you could create another little variable here. You could do something like this, like int count is equal to 0. All right, and if you want, you could do something like this. You could say, okay, every time the loop executes, I'm going to keep track of count, and that will tell me how many times the while loop had to execute in order to find the value that I was looking for. It gives you an idea as to the efficiency of the algorithm. If we do this for the little array, which is what we're passing a length 6, you'll see that it happens pretty quickly. Likewise, if you pass in an array with a whole bunch of values, which even the stuff that you're going to get for the final isn't terribly large. But if you were to pass in an array which had a million values in it, and which, by the way, I think you guys know enough right now how to create such an array, because you could you could create like a little while loop to populate an array of a million values in sorted order fairly quickly. By the way, I think I mentioned this already. Here's one of the caveats with the binary search, is that the array must be sorted. All right. If it's not sorted, the binary search will not work. All right. So let's go try binary search. Binary search. Here we need to use the sorted array. Oops. We need to use the sorted array. And let's search for, so we're searching for the sorted array. Let's search for the value of let's search for the value of 30, because that's in the list. So let's change this to be 30. So this should return 0, 1, 2, 3. This should return, position 3. All right, so 30 was found at position 3. Let's try another one. I'm going to try something at the boundaries. Let's change it to be 50. This will be found at position 5. And 50 was found at position 5. And now let's throw something in here once again that's not in the list. And this will work too, and we'll say 150 not found. So anyway, that's how the binary search works. There are other searching algorithms out there, but we only have enough time to cover the linear and binary search. All right, next thing we do is cover some of the sorting algorithms, starting with the bubble sort, and then we'll finish up with the selection sort. Both of them are fairly efficient, and both of them can be used for either ascending or descending sorting. And the algorithm works like this. So imagine that you have an array. Here's 6 values, right? Element 0 through element 5. The way the bubble sort works is it starts at the beginning, and it looks at the beginning and one value to the right. It looks to see which one of them is, let's assume that we're doing ascending order, looks to see which one of them is smaller. Okay, if one is smaller than the other, it just swaps them. Then it moves over here. Okay. And it does, well, first thing it does, it goes through the entire array one at a time. All right. Then it does the same thing. It'll say, okay, well, now if I go from element 0 up to the end, it looks to see, okay, are there any values that need to be swapped? And if they are, it compares the two, and it swaps the smaller with the larger. Once it does all that, it goes through the array over and over again until it no longer finds any values that need to be swapped. Once it comes across no values that need to be swapped, that means that it must be in order. In this case here, it would be in ascending order. So let's take a look real quick at some of the code to do that. So here's the implementation of the bubble sort, and this is a ascending order. You could do a descending, and same type of idea. You just have to change the relational operators. So what are the parameters? So we're passing in an array and the length of the array. And the first thing we do is we create a little local variable that's called swap, and we initialize it to the value false. All right. As long as we keep swapping values in our array, that means that this will, well, in that case there, then it would be equal to true, and we are then still processing the array. That's what swap is for. Temp, this is just a little local variable that we need to use to allow us to do some like inline swapping of our values. This is a good example where we can use a do while loop. We could make this a while loop if we wanted to, but I think a do while loop works best because we know that we need to process this at least once. Okay, so do while seems to work best here. And what we're going to do is we're going to initialize swap to false, which is already initialized up here, but we're going to reinitialize it again after each iteration of our loop. And what we do is we go from the beginning of our array to the end of our array, right? So as long as it's less than or equal to length minus 1, we don't really need to check the last one because we are going to be, we always need to stop one less than what the end is, because we can never take the last element in the array and compare it to the one that's to the right of that, because then we would be off by 1 and we would generate an error. And this is all we do. All right. So if we're doing this in ascending order, okay, what we do is we check, okay, is the value at the first position greater than the value to the right, okay, which is in the next position? If that's true, then what we need to do is temporarily assign the current value, which is array subscript I, put it in the variable that's called temp. All right. What we're going to do then is say, okay, well, array subscript I is going to now be equal to the value that's to the right. And then, okay, since this is where we're doing a swap, all right, so we're going to say the value on the left is equal to the value on the right. The value on the right is going to equal to what the value on the left was, okay, but we just overwrote it. That's why we're storing in the local variable that's called temp. And now we have swapped, okay, we have swapped these two values. Now we go back up in a loop here, and we'll do that again until we go through the entire array. Once we do that a bunch of times, all right, my for loop will complete, okay, and now we have a while swap clause here. Well, if we ever swapped any values within our array, that means that we made some change, okay, and this will be true. We keep doing this over and over and over again until, okay, we have swap equal to false, right? So if we never swap any values within our array, swap will be equal to false. This will eventually stop. Okay, this is how we know that our array will stop. And then we know that our array will be sorted, and in this case it's in ascending order. If we wanted to be descending, again, do the same type of thing, but you just need to switch your relational operators. One other thing real quick. You'll notice too that the array that's being passed in is not a constant. Okay, it's just an integer array. The reason why it's not a constant because we're doing this all online, and we need to swap the values within the array. So again, this is passed by reference, or passed by pointer, however you want to think of it. All right, so let's do this. Let's just go ahead and do a show you how the sort works. What's the best way to do this? All right, so let's do. We can get rid of this stuff here. Get rid of all this, and we'll do bubble sort. What are we going to pass in first? Let's pass in the unsorted array, and we're going to pass in the size. We actually don't need this any longer either. And now what we're going to do is let's for I is equal to 0, I is less than size, I plus plus. Once we sort the array, let's display let's display the array again so that we can see that it was in fact sorted. So let me do this. Array subscript I equals remember, you know what, let's change the name here. Let's just make this ARR because okay, obviously at first it is unsorted, but then it's going to be sorted, and then I think the variable name becomes a little bit more confusing. So let's just make this ARR just to avoid any confusion here. Right. If I do that, once we display the array, you should see that it is in fact in sorted order, and it is. So we have elements 0 through 5, or all 6 elements, 5, 10, 20, 30, 40, 50. So that's how the bubble sort algorithm works. Pretty efficient. However, it's not as efficient as the next one, which is what's called the selection sort. All right, so with the selection sort is typically more efficient than a bubble sort. The reason is because generally, at least with larger arrays, you have less swapping that takes place. And you may have noticed with the bubble sort, it's like, you know, we swap values, go through the whole array, start all over again, swap some values, start all over again, swap some values, start all over, swap some values. So we can do that over and over again quite a few times. So it becomes fairly inefficient for really large arrays. Selection sort, on the other hand, is a little bit more efficient in the sense that once we process each iteration of the array, what happens is the smallest, again, assuming we're doing ascending order, with the selection sort, the smallest element will be in a first position in the array. Next time we go ahead and process that array, we can disregard the first element in the array and it would just start at the second element. Once we process the array the second time around, we know that the second largest element will be in the second position of our array, and we can disregard that. So the way that it kind of works, and I think I'm glad this is in a book, this is a useful illustration. So imagine this is our original array, 5, 7, 2, 8, 9, 1. First iteration of the selection sort will put the smallest value in the very first position of the array. And what it will do is it'll swap the value that was there previously with the value that it was swapped with. So we would go through this array until we find the very smallest element. Once we find element 1, okay, we take that thing and we swap 1 and 5, okay, with each other, and that is the new arrangement of our array. By doing so, we know that the very first element in my array will now be the smallest value, so I can disregard looking in this position any longer. So you'll see that 1 and 5 were swapped. Next time around, what I do is I start here, okay, and I go from here over to the right, and I look for the smallest element in my array. As I go through, okay, you'll find that 2 is the smallest element. Since 2 is the smallest element, what it will do is it'll swap 2 with the value that's in the second position, so it'll take 2 and 7 and swap them. Third time around, we know that we can just disregard 1 and 2. We look for the next smallest element in my array. So I scan the array, I find 5. 5 is the smallest element. I take 5 and 7 and I swap them. 1, 2, and 5 are now in a proper order. All I have left is 8, 9, and 7. Scan through the array. We find 7 is the smallest value, so we're going to swap 7 with 8. So it'll be 7. Let me go to the next page. 7, 9, and 8. Next time around, again, we can disregard all this stuff because you know that's in the right order. We look at 8 and 9, swap these two values, and then we're done. And that's how the selection start works. Here, I think it's a little bit more confusing to understand logically, but I think once you go through and code this up yourself and read through it a few times, I think you'll get a better feel for how this works. So this is also what's referred to as an inline memory sort, meaning that everything is done in line within the array, and there's no need for any kind of external variables. So here's how the selection sort works. What I'll do is I won't go through all the code line by line. Well, actually, maybe I will real quick. But this exactly maps to the illustration of the diagram that we just saw. So the selection sort is going to have, again, two inputs, the array and the length of the array. And what we do is we have two local variables defined as min index and min value, because we need to know every time we process the array, what is the smallest value that we found and where was it found, right? Which is the min index. And what we do is we have a pair of nested for loops, all right? So nested for loops is fairly common to see in programming. So what we do is we go from the beginning of my array up to one less than the length of the array, because remember, we never want to be off by one, so we never want to look one past, all right, the end of my array. And what I'm going to do is I'm going to say, okay, my minimum index is going to be equal to the start of my array and the minimum value. Okay, we're going to make the assumption that my minimum value is the beginning of the array. And then what we do is we say, all right, from one to the right of that, okay, one to the right of start, let me go ahead and check to see if the value to the right, okay, is less than my minimum value. If it is, then what we're going to do is we're going to swap the minimum value and the minimal index with the current value of I and the current value in an array at that position I. And we're going to do that from this point to the end of my array. Once this for loop is done executing, we know that the minimum index is going to be it's going to be swapped with the value that's at array subscript start. All right, so that's how we're going to do the swap. And we're going to say array subscript start, okay, is equal to my minimum value, meaning that now the beginning of my array for this iteration will contain the smallest value. Next, now what we're going to do is increment start plus plus, right? And now what we're going to do is we're going to start at position 1, okay, and check if that's less than the length minus 1. So every time that we process this array, we don't need to look at the original any values that have been swapped so far to the beginning. So that's what makes it a little more efficient. So again, this might be a little confusing the first time you go around with it, but implement this and execute it 3 times, and I think you'll see how this works. Or you will see how it works. All right, let's go back up into my main here, and now let's do instead of bubble sort, let's do my selection sort. Selection sort, passing in the array and passing in a size. Let's build this thing. Once we're done with it, you'll see that again the array is in sorted order. Right? So we get back the 6 elements, right? 5, 10, 20, 30, 40, 50 in sorted order. So I went a little bit longer today. I think we covered quite a bit. So we have all of our searching and sorting algorithms out of the way. That completes the course essentially. The stuff that I covered for today, you'll need to implement in a final lab, which I'm going to upload shortly. I hope everybody enjoyed this class. I hope you got something out of it. I know everybody at least got something out of it. It's even though this is an intro class, I think there's always something new to learn in this type of stuff. So anyway, any feedback that you guys have, please please let me know. Anything that can be done to improve the course, or anything that you didn't like, please feel free to let me know. I appreciate it. And that's it. So anyway, that completes the course. I'm going to throw up the final lab and some dates up there, which I think I'll instead of me telling you now, I'm gonna put it all in black and white in a little bit, and I think that'll clear things up for you. So anyway, if you decide to take the second half of this course, just so you know, the way that this works is the course pretty much picks up from this point forward. The second half of this course is pretty much dedicated to the concept of structures and classes. How do we create classes and objects? There's some more advanced file input and output that gets done. And what else that I'm thinking of, structures, classes. There's some other types of error handling that gets done. So Oh, and pointers, that's the big thing. The other thing too is we cover pointers and pointer arithmetic and how things are accessed in memory in C and C++ and how it kind of differs from other languages. So quite a bit is covered in the second half of this course. Anyway, if anybody has any questions, feel free to let me know. All right, thank you. Bye-bye.